This is going to be section 13.2, and I have a small demonstration to start this off with. And what I have is this handle which has two different metals. It's called a bimetallic strip. And these two metals are plated right next to each other. And however, each metal, if you remember, conducts heat differently. And metals actually expand. That's what we're looking at. It's called thermal expansion. And so if they conduct heat differently and they also expand at different rates, what's going to happen to this bimetallic strip? So right now you can see that it's starting off fairly straight. I'm going to put this over the heat and see if we can see what might happen with this. So when I turn this, you can see that it's bent. So this is going to explain why this bimetallic strip has bent. So let me go ahead and turn this off and unplug this and remove this to a safer place so I don't get burned. Okay, this is going to be section 13.2. And this is called thermal expansion. So things are going to be expanding as they absorb heat. This shouldn't be a surprise. Gases do this as well. Hot air balloon, the gases inside the balloon will expand. Upon heating, therefore, it's going to enable the density of the air to decrease, so therefore the hot air balloon is going to go up. But this is taking a look at solids. So we'll take a look at liquids in just a few moments as well. So what I'd like you to imagine is instead of solids being packed together, which relatively they are, we're going to be adding something in between them. So imagine you have these four solid particles. And let's say these are the atoms, and they're connected with these miniature springs. So these are the springs. So what's actually happening? Again, they're really packed close to each other, but imagine they have those springs and they're going to be able to move from side to side as well as up and down. When we increase the temperature, remember when we increase the temperature, we're increasing the kinetic energy of the particles. And if you're increasing the kinetic energy of these particles, what's going to start to happen is they're going to start to shake, they're going to start to vibrate faster. And what's going to happen is, since they're on these little springs, they're going to be able to get farther away from each other like this. And they'll also expand in this direction. If you reduce the energy, they'll be all nicely compacted. But as they start to get some more energy, they're going to be moving in all these different directions like this. So if you increase the temperature, you increase the kinetic energy, you're going to increase the velocity. And we've talked about this especially with gases, but that's why we increase the space between the atoms. You increase the space between the atoms, and that's what's providing your expansion. Now, this is on the atomic level, but when you have all these atoms connected, you can imagine you have this giant strip, you're going to have this expansion of the metals on a macroscopic scale. Let me go ahead and show you what's happened now. Returning this back to normal again, and you can see that it should be fairly cool. It's a little bit warm, but it's returned back to its linear state. So why did the bimetallic strip bend? So looking at the bimetallic strip. Well, imagine that you have, again, these two metals that are sitting side by side like this. We have, this looks like copper. This is probably either a zinc or it's probably a steel, iron compound of some sort. But what happens is the iron, as it conducts heat much better, it has a higher expansion. So what's going to happen is these particles over here are going to be vibrating more, and they're going to be increasing their distance more. So what's going to happen is these particles are going to be expanding, and what's going to happen is this length of the metal is going to get longer. It's going to expand as well. But over here, this is the other metal, be it zinc or iron, does not expand as much. They're all going to expand because of the thermal energy, but this one does not expand as much. The end result is, well, since these are attached to each other, what's going to happen is we're going to see this curvature. The end result of it looks something like this. So we draw this curve and then draw those two metals. Draw this curve and then those two metals. Now if I draw some lines like this, what happens is, if you can see in some of them, like this one right here, this is actually a smaller box than this is right here. This should be a smaller box compared to this over here. So these boxes over here are larger, and then they're smaller on the other side. Okay, it's much like if you're on a racetrack. And imagine this is a racetrack, and you want to go around this corner. You have a choice of either going to this inside lane or going to the outside lane. Well, if you go to the inside lane, you'll know, if you've ever driven on a curvy road, the inside lane, you're going to experience a lot more forces than if you were on the outside lane on a curve. Why? Because you're going this distance, and it's actually a shorter distance. It's smaller. It's going to take you longer to go around this over here if you're traveling at the same speed. Okay, if you're traveling at the same speed, this is going to be a sharper turn. This is going to be a less sharp turn. You'll finish this one faster. You'll finish this one a little bit slower because you have a larger distance to travel. Okay, so and that's when you're entering at that same speed. So let's take a look at some of the mathematics behind this. So imagine you have a piece of metal, and it's 10 centimeters long. So right now, the temperature change is equal to 0. This is the normal length. It goes from here to here. If you increase the temperature by 10 degrees Celsius, so if we have a positive delta T is equal to 10 degrees, then what's going to happen is it's going to expand. It expands, let's say, to there. Let's say it expands to 1 centimeter. And then when you add an additional change in temperature of 10 degrees, it also expands. And it expands also 1 centimeter more. So what's interesting about the expansion is proportional to the temperature. If you increase it 10 units, you get this amount of expansion. If you increase it 20, you get double the expansion. So the expansion is proportional to temperature. Let's take a look at another scenario. Let's say we start off with something that's 20 centimeters. Okay, so we have 10 centimeters here and 10 centimeters here. Again, this is going to be the delta T is equal to 0 degrees Celsius. And we're going to go to a temperature change of plus 10 degrees Celsius. What's going to be my thermal expansion? Well, for every 10, it goes 1 when you increase 10 degrees. We have 20 centimeters. So what's going to happen is this is going to increase by a factor of 2 centimeters. So the expansion is proportional to the temperature, but it's also proportional to the original length. So the expansion is proportional. Remember, the alpha is the proportional, symbol for proportional, is proportional to the original length. So we're going to get to a master formula here, and then we'll also take a look at liquids. So the change of length is dependent upon a couple of factors. Okay, we talked about one of the factors being the change in temperature, the original length, but the third factor is actually related to this right here, and it's related to the material. So the change of length is going to be equal to the coefficient alpha, we'll get to that in just a minute, times the initial length, it's going to be my L1, times the change in temperature. So here's my change in length. This alpha is a coefficient, and it's different for different materials. So coefficient is different for different materials. When you see these coefficients also on your homework, they're quite strange. They're not in perfect scientific notation. You'll have something like 26 times 10 to the minus 7th meters per degree Celsius. And why did they put it just 2.6 times 10 to the, whatever. So the coefficients are a little bit strange, and you'll see these. Okay, so we're going to try to rearrange this and solve for a different factor as well. So remember, the change of length is your final length minus the initial length. Oops, I put an I, but that's a 1, so sorry. And then this is going to be equal to the alpha L1 times the change in temperature, which is going to be your T2 minus T1. So this is a master formula to use. This is asking the change in length. But sometimes there might be a question, what is the final length going to be? So with that, you need to know what your initial length is. We can add the initial length to both sides. And what we get is this. We get the final length is going to be equal to whatever the initial length of the metal was, plus the properties of that material, times the original length, times T2 minus T1, or the temperature change. So here's the change in length. Here is the final length. So it's very important that you know which formula that you are using. Liquids are very similar. It's item number 3. Liquids. Liquids also expand as solids expand, as gases also expand. And we have a different formula, but with liquids, you're asking what's the change in volume, not the change in length. So you have your change in volume is going to be equal to, now liquids have different coefficients, so these coefficients are found with the Greek letter beta. This is the coefficient for volumes. So it's the coefficient for different volumes. And again, it will be different for each material, as different liquids will expand at different rates. So instead of length, we're going to be having the initial volume times the change in temperature. So the change in volume will be a factor of the properties of the material and the initial volume and the change in temperature. We can do very similarly over here to calculate for the final volume. Here you're going to have V2 minus V1 is equal to beta times V1 times T2 minus T1. We can add the initial volume to both sides. So while this is going to be a master volume formula for finding the change in volume, we can also be asking what is the final volume? Well, the final volume of material is going to be equal to whatever it started as with the initial volume, plus the amount that it's going to change based upon its coefficient times the initial volume times the final and initial temperatures. So this is going to be the master formula for finding the final volume. That's it for this part.